we have fixed the code. Here's the code. Number of atoms. It has to be even. Did I just change it to odd? It has to be even because, let me show you why. Because we want to start with T1 and end with T1. Okay? Then you need even number of atoms. So you add 2 more, then it's T2 and T1 again. Okay? The number of bonds is odd. Yes, exactly. So T1, what was our number? 2.3, 3.1? It doesn't matter. The important thing is one is higher, the other is lower. Let me remind you what we were doing. We were looking at T1 and T2, like single bond, triple bond. And in principle, when you switch them, when it's infinite, when you switch them, it doesn't matter, right? It's the same band. But it matters when it has edges, okay? So this basically makes sure that we have the proper matrix. And let's go with 100 atoms. 100 atoms. Okay. I will just copy code from here. So what I'm doing is, first I'm going to plot all the energies that I get. Are we in the topologically trivial or non-trivial state? Non-trivial. We start with single bond. So there are a bunch of energies, and then there are 2 solutions that happen at the gap, and then the band continues. Let's see how they look like. So those ones, we can plot their eigenvectors. So figure, let's plot the number 50. Look, it's the edge state. Do you see? It's localized at the edge. Everyone sees it? And then the other one was 51. As you can see, it's yet another state that is localized at the edge. Okay. Let's look at these.
Can you plot any other distance than 50 and 51?
Sure. I was about to plot this one, for example, number 100. Number 100, oops, this is number 10. Number 100 looks like this. Okay, so it's particle in a box all over again. Okay, even if you have an atomic chain, a complicated system, still particle in a box intuition works. Okay, because if you go to the next one, it's a sign. Okay, if you go to the next one, it's the next one. And we can go all the way down to here, which is this one. Okay, so this was topologically non-trivial state. Did you see the topologically non-trivial state, Ata? No? Look, this is bands, these are bands, and there's a topological non-trivial state right in the middle. And when we plot it, we get states localized at the edges. Okay? But if we change, if we make this one 3.1 and this one 2.3 and plot the energies again, there is no edge state. Okay? And even if you plot this one, for example, were you asking for some states near here? No. Okay. Yes, because now we have triple bonds at the edges, and it's a topologically trivial state when you have that one. So we can still plot 50 and 51. We are going to see that they are different. It's not localized at the edges. One final way of thinking about it is this. So we are basically comparing this one with this one. Okay, both have 10 atoms, right? Can you please check? Like this. Now, why? Here is the intuition for you. Okay, take these ones to 0. Okay, and just connect the last one over here. Does it break the pattern of the bulk? No, right? Because it's bond 0, bond 0, bond 0, and then when you connect the last thing, it's the right one, the 0 one. But this one, if you take it to 0, bond 0, bond 0, bond 0, bond 0, bond 0, 0, 0. You see, this one is also 0. So this is topologically non-trivial. Okay? And those accumulation of zeros creates edge states. Okay? But 0, I have exaggerated the weaker bond. Okay? So if the weaker bonds are right at the edges, then you are breaking the pattern. Then it deviates from the bulk. It becomes more edge-like. Everyone is happy? You now know much more about topological states than many people, okay? Because it continues like that. You start with SSH model. Now you can add periodicity on y-axis, and you get a 2D topological material. And you see where it gets to 0, where it gets to band gap, etc. It's very, very nice. Okay, unplanned detour to topological insulators. I was going to talk about graphene and stuff, but let me skip. Should I skip? I did skip. Let me just talk about density of states. Okay? Ata, you can leave. Bye-bye. He was a student who took my course before. For some reason, he was there when I was talking about something new that he hasn't seen. So it was okay for him for that time, but later, no. Because density of states, some of you probably have seen. So what does this mean? Let me give you a simple intuition for them. We just drew a band structure, right? Like this. This is a band structure, and as you can see, I'm only plotting the first Brillouin zone. So density of states are usually measured with respect to energy, and you are basically interested in how many states there are in a certain window of energy. As you can see in this window, there are a bunch of states. There's a peak there. But then if you take the same amount of window, there are less states over there. Do you see it? Whenever the band whenever the band, do you remember the band? Whenever the band becomes horizontal, density of states has a peak. Because in a narrow range of energy, you have a lot of states, right? But whenever the band is really steep, then you have a dip in the density of states. So if we were to draw the density of states of this object, we would get something like that, density of states. Okay? But let's do some math. Let's do density of states for 3D free electron gas. Okay, so we have already done this calculation. Most of this part has been done. Let me show you. When you have a 3D free electron gas, so let's define density of states mathematically. It's number of states per unit energy. Okay, how many states you have per unit energy. Do you remember how to count electrons within an energy range? Do you have any recollection of that? We would make this L, 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 and then there would be different possibilities in each side. You know? Yes? So we would count number of states within some sphere. This was Kx, Ky, Kz, right? And we would count, this would give you, like this K would give you a sphere, a 1/8 of a sphere, 4 pi over 3 K cubed, right? What did we divide it with? We divide it with pi over L cubed. Do you remember this stuff? Yes? So that would give us the number of electrons, total number of electrons, and we multiply by 2 because that's for light. For electron, it's spin, right? Okay, very good. So, say it again.
Is it the 2 pi over L, not L, pi over L?
No, it wasn't 2 pi over L because of the way we treated it. Just trust me, okay? So I have some relationship between N and K, okay? What is that relationship? Can you help me out? You are not going to help me out. I'm just going to copy whatever I have in my notebook, okay? I have L cubed pi squared K squared dk. So if you take the derivative, dk, because we are aiming at this one, okay? So this is the way to go. And we also have E equals to h bar squared k squared over 2m. So when we put all that together, I will just jump to the end. dn over de becomes, look at this complicated stuff, 2 pi squared 2m over h bar 3 over 2 square root e. That's the result. So it's basically proportional to square root of e. Okay? This is density of states of a 3D electron gas. You might think that it's just arbitrarily random thing to ask, but it comes you encounter it over and over. Okay, so it's an important thing. Basically what this tells you is that when you draw density of states, which is dN over dE, with respect to energy, you get something like this. That's proportional to square root of E. Okay? Now, let's talk about density of states for 2D electron gas. DOS for 2D electron gas. Now, this time, the counting changes. Do you remember what happens here? So you have pi k squared over 4 because you now have kx and ky. So you have a quarter of a circle, right? Divided by pi over L squared, and you multiply by 2. This one is easier to interpret because, tell me? I think this is 2 pi. So the thing is that here is the easy way of doing it. E is equal to h bar squared k squared over 2m, right? So this one tells you that dn is equal to L squared over pi times k dk, while this one tells you that dE is equal to h bar squared k dk over 2m. So you can just replace just m. So you can replace this k dk with dE times m over h bar squared, right? So that gives you dN equals to L squared over pi m over h bar squared dE, which tells you that dN over dE is m L squared over pi h bar squared. What is interesting about it? Yes, exactly. It's constant. So the density of states of a 2D electron gas is independent of energy. It's a constant. Okay? Do you have any questions? Finally, you can find the density of states for 1D, which is, I will just write the conclusion here. For 3D, density of states is proportional to square root of E. For 2D, density of states is constant. And for 1D, apparently, density of states is proportional to 1 over square root E. Okay? Finally, since you are now familiar with the idea of density of states, let's talk about also the idea of local density of states. Now, local density of states is something that you see in STM. Okay? So you have some atoms and you have a tip that is going to approach the atom, and depending on the tunneling current, you are going to get some signal, right? Now, that signal is related to the local dose of the system. What do I mean by that? With STM tip, the thing that you can do is you can change the voltage that you are applying. So when you are changing the voltage that you are applying, you are basically looking at different energy windows of the structure. Okay? So try to bring everything together. Okay? There are bands. Okay? Bands corresponds to wave functions. Okay? When you approach with an STM tip, you are basically looking at a slice of a band. Okay? And that slice of a band may create an electron cloud at one place, but not create it at other places. So maybe at a certain voltages, you will see the pi z orbitals of nitrogen. At some other voltage, you will see, let's say, s orbitals of boron. So by playing with this, you can really see the electronic structure of the system. Okay? So that is local density of states. Okay. Do you have any questions? Would it be fair if I ask you in the final to derive density of states for 3D or 2D electron gas? Because I skipped a lot of steps that could motivate you to learn them.
We will still have cheat sheet, right?
You will still have cheat sheet. Okay. Yeah, I will send you a video from previous years where we investigate previous finals, so you will get some idea about the possibility of a final. Finally, I would like to talk about density functional theory. Why you are laughing? I see. So it's a story of the Beauty and the Beast. Okay, the Beast is many body wave function. We already know why this is a beast, right? Because even for nitrogen molecule, we calculated it to have this much bytes, right? So how are we going to calculate anything at all, right? Now, the beauty is DFT, density functional theory, because there is a theorem by Hohenberg and Kohn, 1964. Hohenberg and Kohn tells you the following: there is a one-to-one correspondence between the many body wave function I should really say the ground state many body wave function many body wave function, the ground state many body wave function, sorry. So this should go this should go here, This should come here. The ground state many-body wave function. Maybe this can go also there. Okay. And the ground state electron density. I think this is the only sentence that we actually wrote down. That's the main problem with my lectures and lecture notes. There is some plots there, but nothing written on top of it, right? Yes? Hermitian, yes. That was the other sentence that we actually wrote. So, very good. So here you should really concentrate on this. Okay, DFT is a ground state theory. So this one tells you that, and the derivation of this one is one of the simplest things ever that appeared in physics journals. Yet it led to a Nobel Prize for Kohn, who visited Bilkent back in the days when he was alive. Okay. Good. So what does it tell? Can someone tell me why this is important?
Because we can easily calculate the electron density.
Because we get rid of the curse of dimensionality, right? Electron density is 3D object. You can just take the electron density and let's say you are using 100 grids. So electron density is 1 megabytes. 14 electrons, still 1 megabyte. Because it's total electron density. Okay? So it tells you that there is a one-to-one correspondence between this beast that goes like x1, y1, z1, ... x14, y14, z14. There's only one-to-one. Only one such wave function corresponds to only one electron density. Okay? What does it mean? Since this one results in, this one determines the properties, Ts, it tells you that electron density should be responsible for all properties. But then there is a box, there's a black box in between, which is functional. So you put in, it's not a function, it's a functional. You put in density, it spits out numbers. But the functional is a very general thing. It could involve integrals, derivatives, whatever, like very complicated stuff. But the point that the theory is making in the beginning is that one system can have only one solution in terms of electron density. And that's once you find, so it tells you, for example, that energy is a functional of electron density. If we knew this functional, then life would be super easy. We would easily calculate electronic structure and whatnot. But we don't. We don't know this functional, okay? And this is only the start of the density functional theory. This just tells you that there's hope, okay? What comes next is this. What comes next? I actually have time, so I will also talk about what comes next. There is another paper in 1965, because this one is just, there is hope. Okay, that's it. This one actually tells you what to do with this theory. Okay? In this theory, remember, always keep in mind the difference between many-body wave function, which is entangled, very complicated stuff, and then there are orbitals. Remember the orbitals, which are separate functions, right? So here we start with Kohn-Sham orbitals. Sham orbitals. And Kohn-Sham orbitals are like functions, phi 1, x, y, z, phi 2, x, y, z, etc. Okay? Now, after doing all kinds of trickery, you arrive at Schrödinger-like equation for each of these Kohn-Sham orbitals, okay? Where you have basically h bar squared over 2m del squared over del x squared plus some effective potential times phi I equals ei phi I. So you arrive at Schrödinger-like equation for each orbital. Once you solve this, you get phi i's, okay? Once you take phi I squares, you get the electron density. Once you get the electron density, you put it back into here to get the effective potential. Are you still with me? So you basically solve the electronic problem iteratively. And it's very, very surprising that it results in very good results. It leads to very good results. It's very, very surprising because it's... So what is then missing? Don't we know everything? Well, what we did is we have moved the black box over here to a black box over here. Okay? What we did with these Kohn-Sham orbitals is only take care of, so let's say there is a total energy, right? And total energy has a kinetic part, should I say potential part? Let's go with potential part. I'm not sure about this one. Let me just say kinetic part and the rest. What we did with this treatment is that this takes into account most of the kinetic energy part. So we are basically saying that this is the electron density, and since this is the electron density, we are basically taking this part. Then in the rest, there is especially the exchange part and the correlation part. Exchange part is the thing that comes from the spin stuff. Do you remember the spins couldn't be together, etc.? Correlation part is, again, once you included everything, whatever is left is the rest. So that's the correlation part. Now, where do you get these exchange correlation functionals? Where do you get them? You need functionals for them, right? You do some approximations. For example, you take an electron gas, free electron gas, calculate exchange for that electron gas when you change the density of electron gas. Are you following? Yes? You change the density, you find the energies, and you assume that wherever you find a certain density, you should put that much energy there. Okay? That's called local density approximation. Local density approximation. And this was hugely successful. Then you improve it. You now include not only the density itself as a parameter, but also the derivative of the density, how it changes in space, then you get generalized gradient approximation. Let me just show you one person. John Perdue. He is the best cook of the of these functionals. Look at this. So this is the GGA, generalized gradient approximation made simple. 181,181. It's like a joking level of. Look, he gets 32,000 citations every year. Okay? Yes, I think so. No. He's just cooking this stuff in a right way. So, I mean, if you go to Kohn, Walter Kohn, probably he doesn't have this many citations. What prize? Walter Kohn. Yes. Not John Perdue. Okay, I don't see his scholar, but yes, I think he doesn't have. But in any case, these are the studies you see in the 90s. Okay, something huge happened suddenly, and immediately Walter Kohn got the Nobel Prize, because once they saw that it is working, and I don't need to show you any other proof than this. Is he still publishing? Yes, he is. The predictive power of exact constraints and appropriate norms in density functional theory. Understand density-driven errors for reaction barrier heights. Let's see something that. Okay, DFT exchange, sharing perspective on the workhorse of quantum chemistry and material science. Elevating density functional theory. Elevating. To chemical accuracy for water simulations through a density-corrected many-body formalism. So they are really at the kitchen of this thing, and me personally, I'm eating. I mean, they are preparing density functionals, and we are just using them in our calculations. Okay? And we cite them. Okay. Any questions? Comments? Okay, thank you very much for your attention, and let's continue with the presentations. Good luck.